All right, so we're going to talk about trigonometric equations. We'll spend a few sections talking about this concept. Uh, so let's get into it. Um, I take a little bit of a different approach than the approach that the book takes to this, and we'll see why in the next section. Uh, so consequently, I usually try to give you different examples than the examples that are in the book, but for this section, I'm going to give you the same exact examples that are in the textbook, so that you can go and kind of compare how the textbook approaches these problems, in case you like, I guess, their approach better. Um, but so anyway, um, but I prefer my method, obviously, and and hopefully you'll see why when we get into multiple angle stuff in 6.3. So, okay, so here's the approach that I take. First of all, it requires us to establish certain facts about the way that trig equations work. So, um, and the first one is this. If you have an equation that says sine x equals k, then you get two different infinite sets of solutions to this equation, right? Assuming, of course, that k is an appropriate value. So if k is between -1 and 1. If k is like 5 or something, then sine x equals 5, has no solution. But if k is an appropriate value, then um, then one set of solutions that you get is that x is just sine inverse of k, all right? But then you also have every 2 pi units after that or before that is also going to be a solution to the equation, all right? Um, the other set of solutions is that x could be pi minus sine inverse of k, all right? And then, of course, every integer multiple of 2 pi units after that as well, okay? So to see why this is true, clearly one solution to sine x equals k is x equals sine inverse of k, right? That is obviously one solution, right? You just take sine inverse of both sides, sine inverse of sine, those will cancel, you'll get x equals sine inverse of k. So that's pretty clear. Now, since sine is periodic with period 2 pi, we're going to get another solution every 2 pi units after that, and that's where the plus 2n pi comes from, where n is an integer, right? Maybe you've never seen this notation, but anyway, this just means n is an integer. Okay, as for the other set of solutions, so I'm talking about this set right here, the pi minus sine inverse of k. To see why that's also going to be a solution, note that if k is greater than 0, remember that sine goes with your y values. So if k is greater than 0, in other words, if k is positive, so y is positive, that means that sine x would have to be, or rather, x itself would have to be either in quadrant 1 or quadrant 2. Okay? If x is in quadrant 1, then x is just sine inverse of k, right? But if x is in quadrant 2, then sine inverse of k would actually be this reference angle right here, okay? Because sine k is going to be positive, it's always going to return a value in quadrant 1. So it's going to be this acute angle right here, which means x is actually pi minus sine inverse of k, right? So this portion of the angle is going to be the entire straight angle pi minus this portion of the angle, so pi minus sine inverse of k. That's if k is positive. Now, what if k is negative? Well, if k is negative, then then that means sine x is a negative value. That would put you in quadrant 3 or quadrant 4. Now, if you're in quadrant 4, then x is going to be this negative angle right here, which is just sine inverse of k. Okay, so that's where you're going to get one set of solutions. The other set of solutions is going to happen if you're in quadrant 3. If x, the angle x, is in quadrant 3. Now, if that's the case, remember that sine inverse of k is this negative angle right here. So if you do pi minus sine inverse of k, that would be, you'd be subtracting a negative value. So you would really be adding on a little bit of a value. And this angle the angle that you would be adding on is sine inverse of k, right? This reference angle is the same as that one. So only, I guess, well, no, it is. It's exactly the same reference angle, so it would be going in this direction. Okay, so it's x minus sine inverse of k. Or sorry, it's pi minus sine inverse of k. So whether k is positive or negative, you're always going to get those two possibilities, that x is sine inverse of k or that x is pi minus sine inverse of k. Now there are some details with, well, what happens if, x is a quadrantal angle? But the rule still works in those cases, right? And we'll see some examples of this, okay, going forward. So that's how we're going to treat, like anytime you see an equation that's of the form sine x equals k, we're just automatically going to jump to this fact. So this is a fact that you have to memorize, okay? But this is the reasoning behind it. So if you understand the reasoning behind it, then there's actually less memorization to do. But anyway, we can go through a similar line of reasoning for cosine and tangent. And we get similar but not exactly identical rules, okay? So for equations of the form cosine x equals k, we're going to get two sets of equations, x equals cosine inverse of k plus 2n pi, or x equals 2 pi minus cosine inverse of k plus 2n pi. All right? So notice the difference, right? Here, for a sine x equals k situation, the other solution is pi minus sine inverse of k. For the cosine x equals k situation, the other solution is 2 pi minus cosine inverse of k. And just to draw you kind of a quick sketch as to why that would be true, notice that if cosine goes with your x values, so if k is positive, then x would be either in quadrant 1 or quadrant 4, right? Not quadrant 1 or quadrant 2, because cosine goes with your x values, so x is positive. All right, so that means if you're dealing in quadrant 1, this is just cosine inverse of k. But if you're dealing with this angle here in quadrant 4, the reference angle is still cosine inverse of k. So then the angle x would actually be 2 pi minus cosine inverse of k, right? So 2 pi minus cosine inverse of k. And then you could draw a similar picture for what happens if you're in quadrants 2 or 3, right? That would happen if k is negative. But you get the same rule, right? This is the other possibility. And then finally, for the tangent case, if tangent x equals k, then x equals tangent, sorry, excuse me, x equals tangent inverse of k plus n pi. Notice that the period here is only pi instead of 2 pi. Well, that's because the tangent function has a period of pi instead of a period of 2 pi. And then notice that you also don't get a separate set of solutions. You only have this one set of solutions. Well, that's because if we go through a similar line of reasoning, if k is positive, then that means that x is either in quadrant 1 or quadrant 3, right? And so the solutions are exactly pi units apart. So you get both solutions by just adding n pi, right, rather than adding 2n pi. It only works for the tangent case, though. Okay. Anyway, so that's the idea. And so our strategy for solving trig equations, or at least the strategy that I'm going to apply, is given any trig equation, I'm going to try to get it to look like one of these three forms. And then once I've got it in one of these three forms, I can apply these rules, okay? Well, the appropriate rule for the situation that I'm dealing with, okay? So I've got 5 examples that I want to walk you through. So let's get to it. Okay, so let's solve 2 sine theta plus 1 equals 0. Okay, so my goal is to get this to look like sine x equals k. Or in this case, the variable is theta. So we'll say sine theta equals some number. So I'm going to isolate the sine theta first and foremost. And you can do that using any of the tricks that you learned from algebra, right? Back from your algebra days. So in this case, we're going to move the 1 over. and then we're going to divide by 2. Okay? So now we've done it, right? We've isolated this. We've got it in the form, sine something equals something else, right? Sine x equals k. Or in this case, we've got more specifically sine theta equals -1/2. So since we've got it in that format, now we can apply this rule here, right? We've got sine x equals k. If that's true, then either x equals sine inverse of k, plus 2n pi, or x equals pi minus sine inverse of k, right, plus 2n pi. So I'm going to get theta equals sine inverse of -1/2, right, plus 2n pi, or theta equals pi minus sine inverse of -1/2 plus 2n pi. Now, sine inverse of -1/2 you could do in your head, but you're welcome to use your calculator as well. What would you get? I think you would get -pi/6, right? Sine inverse of -1/2 is -pi/6. Yep. So you get theta equals -pi/6 plus 2n pi, or theta equals pi minus -pi/6 plus 2n pi. All right. So pi minus -pi/6, that would be 7pi/6. So 7pi/6 plus 2n pi. Okay, and those are your solutions. So if you wanted to list off all of the solutions, right? So if you wanted to list off all of the solutions, they would be -pi/6 plus 2n pi, or 7pi/6 plus 2n pi, where n is an integer. And I'm just going to use that symbol to say n is an integer. In other words, a positive or negative whole number. So what we're saying is that, so what this means is that you can take turns replacing n with any positive or negative whole number, and you're going to generate a whole list of solutions. So this set equals, like if I deal with this first rule, if I plug in like -1 for n, so I'm going to get a whole bunch of solutions. Maybe I should say it like this. Maybe I should say, so this equals, if I plug in -1 for n, I'm going to get, what would this be? 2 pi. So that would be 12pi/6, right? So -12pi/6 times -pi/6 is -13pi/6. That's if I plug in -1 for n. If I plug in 0 for n, and maybe I should have said ... right? There's a whole bunch of solutions that come before it, because I could plug in -3, -2, -1. Then if I plug in 0, I'm going to get just -pi/6. And if I plug in 1, then I'm going to get 12pi/6 minus pi, so 11pi/6, right? And so forth. And those are all solutions that are just generated from this first value, right? Or from this first set of solutions. Now, the second one is also going to generate another list of solutions, right? So I'm going to say, all right, so then we generate all these ones, and then we're going to start to generate these ones, right? So if I plug in, -3, -2, if I plug in -1, I'm going to have 7pi/6 minus 12pi/6, so that's what, 5pi/6. Is that right? Hold on. 7pi/6 minus, so sorry, -5pi/6 is what I meant. -5pi/6. And then if I plug in 0 for n, I'm going to get 7pi/6. And then if I plug in 1 for n, 12 plus 7 is 9. No, 12 plus 7 is, 19. So I get 19pi/6, right? And so forth. Okay, so I get a whole bunch of solutions, infinitely many solutions. I get one set of infinite solutions generated from this rule, and another set of infinite solutions generated from this other rule. Okay, and that's all of my solutions. Now, oftentimes, we're only interested in the solutions that live between 0 and 2 pi, right? So say solve, then list the solutions in the interval from 0 to 2 pi. Okay, so this is all the solutions. So the ones that live in the interval from 0 to 2 pi Well, it wouldn't be negative 13 pi over 6, that's less than 0. It wouldn't be negative pi over 6, that's less than 0. 11 pi over 6, though. Remember, 2 pi is the same as 12 pi over 6, so 11 pi over 6 is in there. So I get 11 pi over 6. Anything more than that, like if I add another 2 pi to that, 2 pi plus 11 pi over 6 is obviously going to be more than 2 pi. So the next solution that's generated from this rule is going to fall outside the interval. So 11 pi over 6 is the only one. What about this one over here? Okay, so this is obviously less than 0, so it doesn't work. 7 pi over 6 is in the interval. 19 pi over 6, well, that's more than 2 pi. That's right, 2 pi is 12 pi over 6. That's too much. So those are the only two solutions that we get that live in the interval from 0 to 2 pi. Okay, so these are all of the solutions. And these are the ones that live between 0 and 2 pi. The other thing that I want to say about this before I give you another example is that obviously the same thing goes for like if you're working in degrees. So if the directions had said, solve and then list all the solutions between 0 degrees and 360 degrees, right? Then you would go about doing the same thing, and these rules right here that we've written out, instead of 2n pi, you would just say 360 degrees, right? 360 degrees, 360 degrees. 360. Here you would say 180 degrees, okay? So the same thing applies when you're dealing with degrees rather than radians. But I'm just going to stick to radians for the examples that I show you here. I trust that you can do this with degrees as well. Okay, so here's another one. Let's do sine theta tangent theta equals tangent theta. Okay. So remember, our goal is to get this to look like one of these forms over here, right? We want it to look like sine x equals k, cosine x equals k, or tangent x equals k. So the way that I'm going to do that here is by factoring. So I'm going to move everything over. So this is a common technique from algebra, right? You move everything over, and then you factor. In this case, I can factor out a tangent theta. Okay. The reason that you do that is because now you have a statement that says this thing times this other thing equals 0. The only way that can possibly be true is if one of the things is 0. So either tangent theta is 0 or sine theta minus 1 is 0, right? That's the zero product principle. So okay, so I'm going to say tangent theta equals 0, and then maybe leave myself some space, or sine theta minus 1 equals 0. Okay, so now I've split it up into two easier equations to solve. In fact, this one's already in the format that we like, tangent x equals k. This one's really close. All I have to do is move the 1 over. Sine theta equals 1. Okay, and now they're both in the kind of format that I like. Tangent theta equals 0 or sine theta equals 1. Okay? So I'm not done, of course. I haven't solved for theta, but I can apply the rules now, right? I can say in the tangent case, all right, if tangent theta equals 0, then theta equals tangent inverse of 0 plus n pi. And that's the only solution that you get. Remember, tangent only has one set of solutions because the period is pi instead of 2 pi. For the sine theta equals 1, I'm going to say theta equals sine inverse of 1 plus 2n pi, or theta equals pi minus sine inverse of 1 plus 2n pi. Okay, the rest is history. I mean, the rest is pretty easy from there, right? Tangent inverse of 0 is 0, right? So in other words, we get 0 plus n pi. Well, that's just n pi, right? So that's one set of solutions. Sine inverse of 1 would be pi over 2, right? So we're going to get theta equals pi over 2 plus 2n pi, or theta equals pi minus pi over 2 plus 2n pi. Well, notice that pi minus pi over 2 is just pi over 2. So for this second kind of equation that we've solved here, we're discovering that either theta equals pi over 2 plus 2n pi, or theta equals pi over 2 plus 2n pi. Well, that's just repetitive, right? It's like you don't get any extra information from this second statement. It's not that it's wrong, it's just that it's redundant, right? So really we get these two solutions, n pi or pi over 2 plus 2n pi. So if I want to list off all of my solutions, it would be any angle of the form n pi or any angle of the form pi over 2 plus 2n pi, where n is an integer. Okay, and then if I want to list off the ones that live between 0 and 2 pi, well, if I plug in -1 for n, here I'm going to get negative pi. That's too small, right? If I plug in 0 for n, I get 0. That's in the interval. If I plug in 1 for n, I get pi. That's also in the interval. And if I plug in 2 for n, I get 2 pi. That's not in the interval, right? Because this parenthesis indicates that you can have any angle up to 2 pi, just not including 2 pi. So 2 pi is not going to be in here. From this set of solutions, if I plug in, say, -1, I'll have pi over 2 minus 2 pi. That's obviously less than 0. If I plug in 0 for n, I'm just going to get pi over 2. That's in the interval. Okay. If I plug in 1 for n, I'm going to have pi over 2 plus 2 pi. That's obviously bigger than 2 pi. So that's as large as that one's going to get. Right, so here are all of the solutions, and then here are the ones that live between 0 and 2 pi. Okay. Okay, let's do another one. So let's do tangent squared x plus tangent x minus 2 equals 0. Go ahead and give the video a pause and see if you can do that one on your own. Okay. I think we can factor this one as well. I think we can call it tan x plus 2 times tan x minus 1 equals 0, right? That'll give us a 2 tangent x minus the tangent x. That gives us the 1 tangent x in the middle. And then, of course, the -2. So that does the trick. So now I'm going to apply zero product principle, right? Say tangent x plus 2 equals 0, or tangent x minus 1 equals 0. So I'm going to get tangent x equals -2, or tangent x equals 1. Okay, so this means that x equals tangent inverse of -2 plus n pi, or x equals tangent inverse of 1 plus n pi. Now this one we can do in our heads. Tangent inverse of 1 is pi over 4. This one we can't, though. Tangent inverse of -2 I think is something probably kind of nasty. So I'm just going to leave it in this format, and I'm done, right? So x is pi over 4 plus n pi, and then x is, the exact value is tangent inverse of -2. So if I want to list off all of my solutions, they're going to be tangent inverse of -2 plus n pi, and then pi over 4 plus n pi, where n is an integer. Now, if you're interested in knowing about how much that is, tangent inverse of 2, you can pop that into your calculator. Sorry, tangent inverse of -2. That's approximately -1.1, we'll say. So this is about -1.1 plus n pi, and then, of course, pi over 4 plus n pi. Okay. So that's all of the solutions. Now, if you're interested in the solutions that live in the interval from 0 to 2 pi? Well, so for tangent inverse of negative 2, you're going to get negative 1.1. So if you plug in like negative 1 for n, that's going to be too small. If you plug in 0 for n, that's still going to be too small. If you plug in 1 for n, so let's see, tangent inverse of negative 2 plus pi is 2.03. And remember that 2 pi is going to be like 6.28-ish. So 2.03 is well within that range. I'm going to say 2.03 approximately. Or actually, let me give you the exact values, right? So the exact values are, tangent inverse of negative 2 plus pi. And then I'll give you the approximations in a second. What if we add 2 pi, right? Because tangent inverse of negative 2 is a negative number, so when we add 2 pi, we'll get an answer that's less than 2 pi still. So if we add, so if we say, tangent inverse of negative 2 plus 2 pi, then we get 5.17 or whatever, but that's well within the range still. Tangent inverse of negative 2 plus 2 pi is going to be in there. And then for this, and that'll be it. If we go up to 3 pi, 3 pi is going to be too big, right? Here, if we plug in something negative, pi over 4 minus pi is less than 0, so that's not going to work. If we plug in 0, we're going to get pi over 4. That works. If we plug in 1, we'll get pi plus pi over 4. That would be 5 pi over 4, right? That's within the interval. 2 pi is 8 pi over 4, right? So 5 pi over 4 is well within there. And then if we go up to 2 pi, obviously 2 pi plus pi over 4 is more than 2 pi. So that'll do it, right? That's all of them. But now if I want the approximations, I can say, well, this is approximately. Tangent inverse of negative 2 plus pi was about 2.03. Tangent inverse of negative 2 plus 2 pi was about 5.18, right? So 5.18 approximately. I suppose we could approximate pi over 4. Pi over 4 is about 0.79, and 5 pi over 4 is about 3.93. Okay, so those are the approximate solutions that live between 0 and 2 pi. Anyway, so that's that one. Okay, let me give you a couple more. So let me show you what to do in the case. So we've seen examples with sine, we've seen examples with tangent. We haven't seen any examples with cosine. Hopefully we'll get to one of those here in a second. But what I want to do is show you, what if you were given like a cosecant or a cotangent or something like that, right? What do you do? Well, for those, you can use reciprocal identities, of course, right? Okay. So let's see if we can solve something involving a cotangent. You might be tempted to say, look, it's already factored. We can say cotangent x equals 1 or cotangent x plus 3 equals 1. But that would be wrong, okay? What you're attempting to do is you're attempting to apply the zero product principle. The problem is that this product is not equal to 0. So the zero product principle doesn't apply. It's not the case that if you multiply two things together and get 1, that one of these things has to be 1. For instance, this could be 1/2 and this could be 2. And 1/2 times 2 is still 1, right? So it's not the case that cotangent x has to equal 1 or cotangent x plus 3 has to equal 1. Unfortunately, it's more work than that. What we need to do actually is distribute the cotangent x, then move the 1 over, and then see if we can refactor it. So I'm going to get cotangent squared x plus 3 cotangent x equals 1. And then if I move the 1 over, I'm going to get cotangent squared x plus 3 cotangent x minus 1 equals 0. Now, this thing I don't think is going to factor, because look, in order to factor, you're going to have a plus 1 and a minus 1. So your first sort of entries would have to be cotangent x and cotangent x. And then the last ones would have to be -1 and +1, but that's not going to give you a 3 cotangent x in the middle. So what do we do about this? Well, notice that this is quadratic in form, right? Like if we said let u equal cotangent x, then what we would have here is u squared plus 3u minus 1 equals 0. So where u equals cotangent x, right? So if we can solve this equation for u, then we can go ahead and back substitute and put in u equals cotangent x. So that's one way that you could do it. Now, another way that you could do that, in order to solve this thing for u, since it's not factorable, you have to use quadratic formula. And quadratic formula is just going to say, you know, u equals -3 plus or minus square root of 3 squared minus 4 times 1 times -1 over 2 times 1. But you're just going to end up going back and back substituting u equals cotangent x. So instead of saying u equals blah blah blah, why not just say cotangent x equals blah blah blah? That's how I'm going to do it, right? So I'm going to say, if this is the case, then cotangent x equals -3 plus or minus the square root of 3 squared minus 4 times 1 times -1. So that should actually just make it a plus 4, right? Over 2 times 1. Okay. So in other words, cotangent x equals -3 plus or minus the square root of 13 over 2. Okay. Now, to get this in one of the formats that we like here, right? Sine, cosine, tangent. Right? To get it to look like one of those, you just apply a reciprocal identity, right? So if cotangent x equals this stuff, that means tangent x equals 2 over -3 plus or minus root 13. And you don't have to bother like trying to rationalize this or anything, okay? Because you're going to have to use a calculator to figure out, to get an approximation for tangent inverse of this stuff anyway. But so now we're almost done solving. We can say, all right, so x equals tangent inverse, and I'm actually going to split this up. Right, this is two separate numbers. It's 2 over -3 plus root 13, and then it's 2 over -3 minus root 13. So I'm going to split up my solutions that way. I'm going to say, okay, so x equals tangent inverse of 2 over -3 plus root 13 plus n pi, or x equals tangent inverse of 2 over -3 minus root 13 plus n pi. And there you go. That's your solution set. Those are the exact values. If you want, you can get approximations. And that's what I'm going to do. So let's see. Tangent inverse of 2 over -3 plus root 13 is about 1.28. This is about 1.28 plus n pi, or x is approximately tangent inverse of -3. Tangent inverse of 2 over -3 minus root 13 is about -0.29 plus n pi. Okay, so those are the exact values. So if you wanted to list off all of the solutions, or sorry, those are the approximate values. So if you wanted to list off all the solutions, you would say, well, you know, it's approximately 1.28 plus n pi, and then -0.29 plus n pi. If you want to get the solutions that live between 0 and 2 pi, well, you do the same thing as what we've been doing, right? So if I plug in So pi is about 3.14. If I plug in a negative 1, I'll be subtracting 3.14 and I'll get a negative value, so that's too small. If I plug in 0 though, I get 1.28 and that works. If I plug in 1, 1.28 plus pi is about 4.42. That's still less than 6.28, so that works. If I plug in 3 pi, if I plug in 3, that's obviously going to be more than 2 pi. Or sorry, if I plug in 2 for n. Here I plugged in 0, here I plugged in 1. If I plug in 2, that's obviously going to be more than 2 pi, so I'm not going to go all the way there. Here, if I plug in negative 1, it's going to be too small. If I plug in 0, it's going to be too small. If I plug in 1, negative 0.29 plus pi is 2.85 approximately. And if I plug in 2 for n, then I get about 5.99. If I plug in 3 for n, that's going to be too much. Okay, so I get 4 solutions that live between 0 and 2 pi for that particular problem. Okay, one more. Let's do tangent x plus root 3 equals secant x. Okay, so this one is a little bit tricky. If I move the secant x over and then try to factor, I don't really see a lot of opportunity for that. I suppose if I move the secant over, I could think of it as 1 over cosine, and I could think of this as sine over cosine. So then I could actually subtract them. I could say it would be sine x minus 1 over cosine x plus root 3 equals 0. I don't know, that's maybe worth exploring, but I think we're going to end up going in circles. Let's just explore that. Let's just explore that. I have another idea for how to solve it if this doesn't work, but I'm just curious. So this is secretly sine over cosine, right? Right, it's secretly sine over cosine, and this is secretly 1 over cosine. So I can subtract again. Sine minus 1 is just sine x minus 1 over cosine x. I'm not sure how helpful that really is. I mean, I suppose, I suppose we could multiply through by cosine x now to clear the fractions and get sine x minus 1 plus root 3 cosine x equals 0, but it's still just as hopeless. Like trying to factor that, I think, is still equally a hopeless task. So I don't know if that's the best way to do it. Here's what you can do. So we can go ahead and square both sides of this equation. So I'm going to square both sides. And let's see. Remember, you can't just distribute the two. You have to write this out twice and FOIL it. So if I imagine do that, I'm going to have tangent x times tangent x. That's going to be tangent squared x. Then I'm going to have tangent x times root 3, and then I'm going to have a root 3 times tangent x. So that's in total going to give me 2 root 3 tangent x. And then I'm going to have a root 3 times a root 3, and that'll just be 3. Okay. Now, my motivation for doing this is that if I can get, what I don't like about the original equation in black ink is that I have 2 different trig functions going on, and I can't factor them in such a way that that I end up with, you know, a nice little equation like this. And so I need to try to do something. I need to try to do something to rewrite this equation so that it's all just in terms of the same trig function, right? By squaring both sides, I end up with a tangent squared and a secant squared. And whenever you see those two things together, your mind should be going to Pythagorean identities, right? So there's a Pythagorean identity that deals with tangent squared and secant squared, right? We know that tangent squared theta plus 1 is equal to secant squared theta. So we can make a decision now whether we want to rewrite this whole thing in terms of tangent or secant. because I can rewrite the tangent squared. I can rewrite that as secant squared minus 1, or I could rewrite the tangent squared as I can rewrite the secant squared as tangent squared plus 1. My feeling is that because you have a tangent to the first power here, that you're not going to be able to rewrite quite as easily. My feeling would be it's probably best to rewrite this in terms of tangent. So then everything's in terms of the tangent function. So let's do that. Okay, and now what's really nice about that is notice that the tangent squareds are going to cancel now, right? Like if I subtract the tangent x over to the other side. Um, so after canceling those off, now I just have 2 root 3 tangent x plus 3 equals 1. That's not quadratic anymore. I can just solve for tangent x by moving the 3 over here. So I'm going to subtract 3 and get 2 root 3 tangent x equals negative 2. And then I can divide through by 2 root 3. And I'm going to get tangent x equals negative 2 over 2 root 3. That's just negative 1 over root 3. Or if you prefer the rationalized version, that would be negative root 3 over 3. But there you go. Like, that's all there is to it. From there, the rest is history. The rest is easy. Well, one thing that I will mention about this is that anytime you square both sides of an equation, you allow for the possibility that you've introduced extraneous solutions. And so one thing that you should do when you finish this is you should go back and check your solutions and make sure that they actually work in the original black ink equation. Okay, so let's finish it out and see what we get. So we're going to get x equals tangent inverse of negative 1 over root 3 plus n pi. And that's it for this particular equation. That's the only set of solutions that we're going to generate. So, okay, so tangent inverse of negative 1 over root 3 is negative pi over 6. Okay, so this is negative pi over 6 plus n pi. So let's check those, right? Like if I plug in negative pi over 6 to the original equation, tangent of negative pi over 6 is of course negative 1 over root 3. So this would be, negative 1 over root 3. Secant of negative pi over 6. Well, secant is 1 over cosine, right? Cosine of negative pi over 6 would be root 3 over 2. So this would be 2 over root 3. Oh, is that right? Yeah, that's right. Yeah. Okay. So is it the case that negative 1 over root 3, negative 1 over root 3 plus root 3 equals, okay, so it equals 2 root 3 over 3. Is that the same as 2 over root 3? Yes, if you rationalize this, you multiply by root 3 over root 3, you get 2 root 3 over 3. So yeah, so this checks out. Okay. I guess we could ask ourselves if the one, so this is a solution in quadrant 4, so the other solution must be in quadrant 2. We could ask ourselves if the solution in quadrant 2 also works. So maybe if we add pi, we would get 5 pi over 6, right? So is it also true that tangent of 5, well yeah, tangent 5 pi over 6 would still be negative 1 over root 3. Secant of, but this is interesting, secant of 5 pi over 6 would be negative 2 over root 3. So, so I think that the other solution here is extraneous, in fact, right? So, yeah, let's verify. So I'm going to just plug it into my calculator. Tangent of 5 pi over 6 plus root 3. that equals 2 root 3 over 3. Secant, so I'm going to say 1 over cosine of 5 pi over 6 is negative 2 root 3 over 3. You see that? So you don't get the same thing. Okay, so what that tells me is that actually, for this particular equation, the solutions in quadrant 2 are extraneous. They're not actually solutions to the original equation. And again, we introduced those extraneous solutions because we squared both sides. So I think that really what we need to do, so I'll say this. Note, when n is odd, tangent inverse of negative 1 over root 3 plus n pi is in Q2, and those solutions are extraneous. Okay, therefore the solution set should really be only the even multiples of pi, so not the odd multiples of pi, only the even ones. So really the solution set is going to be, sorry, I don't know why I wrote it tangent inverse, it's just negative pi over 6, right? But anyway, the solution set would be negative pi over 6 plus n pi, or plus 2 n pi. Okay, so there's the solution set there. Okay, so that's all I have to say for this section. What I'll point out is that in each of these cases, the arguments were always just x, right? Tangent x, secant x, cotangent x, etc. In the next section, we'll talk about what to do when you have like x plus 3 pi, or 2x minus pi over 2, or whatever. So we'll talk about those kinds of situations, as well as some other things. The other thing I'll point out is that I lied. We did not ever look at a cosine problem. So just be aware of the fact that when you're dealing with a trig equation involving cosine, that the other solution is 2 pi minus cosine inverse of k, not just pi minus sine inverse of k. Again, don't blame me, blame the book. I'm using the same examples as the book so that you can look at the book and see the way that they approach it, because they do approach these problems quite a bit differently than I do. Okay, that's all I'm going to say about that.